4, 4, and it says part 1, but both parts are together. So I'll just erase that. Alright, section 4, 4 is properties of definite integrals and more area props. So this has more to do with, again, what the area represents, and what we're going to get to is the area between curves. And the area of when we can add areas. Alright, so properties of definite intervals, more area. So this has more to do with what the area represents. Alright, the first one, which again, it should make logical that we can solve these cases because of how areas work. Alright, so when we solve definite integrals by hand and graphically, so again, you should be able to do both, solve them by hand and graphically using the calculator. Now, you can use the graphing calculator on applications, any applications you want. The only time you have to do it by hand is when I specifically say solve it by hand. And I will ask you to solve it by hand on the quiz and the test. Alright, so you can find it continuous, if your function is continuous over a to b, f of x is any antiderivative, so remember this is the definite integral, right? So remember, what it literally is, it's the sum of all of the function values over that continuous interval a to b. So it's adding up all of the function values between a and b. So if the function values are positive, we get a positive increase. If the function values are negative, we get a decrease, right? When we find the difference between the two. Right, so the area above is increase, area below is decrease. Right, more properties. Well, suppose I want two functions and I want to add them together. All right, so suppose I know that if I have my interval a to b, and I integrate it from a to c, and then I integrate it from c to b, and it specifically has to be this way. C is in the middle. C is between a and c is in the middle there. Well, it should make sense that it is the same as if I do the two integrations from a to c and then from c to b, that's the exact same area as integrating from a to b. And the reason why we might have to do it this way, and again, I'll do an example of it, is if my graph is defined by two different functions, right? A piecewise function from a to c and c to b, right? I can't integrate this function if it's represented by two different functions. And so something like this, like an example like this. All right, suppose that maybe my first function's a parabola, quadratic type shape, and then at c, it switches to a line. All right, so I've got two different parts here. I want to find the area from a to b, right? So I want to find this total area here, which I would integrate my function f of x, would integrate from a to b, f of x dx. But what we run into is, remember, the derivative doesn't exist here at this corner. And so what happens is we get an error if we try to do that. We have to split it into the two different pictures. We take area 1 here, area 2 here, and we get that integrating from a to c, f of x dx. Add it to area c to b, f of x dx. And when I do that, I can now solve the area. I can find the total area, but I do have to break it down into two separate integrations. This also is true is if I want to find the area above or below the x-axis. So suppose, I'm going to go and draw a different picture over here. Suppose we were looking at something like this. Alright, so this would be C. This would be my C. Suppose this is A and this is B. Well, what if I, when we did those area examples where we're given the graph and we knew the area above was 72, area below was maybe 25. Well, how we figure that out is we find the individual area. I find this area here and this area here. Right? I'd find my area 1 by integrating a to c f of x dx. I would find my area 2 by integrating c to b f of x dx. This one would come out negative, right? Because it's below. But if I took the absolute value of it, I would know what that area is. So suppose it came out negative 15. I'll take the absolute value. It means the area would be 15. This area equals 15. Right, and that's one way where we could also use this. And then I know if I add the two areas together, I get my total area. It's one way we can use this. Alright, so we'll do an example of a piecewise function in this case. Alright, so an example of a piecewise function. Alright, this is where we have to use this method. Alright, my function f of x is defined differently on different parts of its domain. That's what a piecewise function means. For values of x that are smaller than 3, it's on the x squared function. For values of x that are equal to 3 or bigger than 3, it's on the 27 divided by x function. All right, on that part of the function. And so I want to find the area under the graph from 1 to 5. Notice, from 1 to 3, we would use the x squared function. Then, from 3 to 5, it would be the 27 over x function. And so that's why we would have to graph it differently. Or when we, and I'll show you graph it, not graph it differently. That is why we have to do 2 integrations. I can't integrate from 1 to 5, because at 3, it switches from one function to a different function. And so if I wanted to find the area under the graph of x, f of x, I have to find the area from 1 to 3 using the x squared function. Add to that, integrating from 3 to 5 of my 27 over x. And it's okay that I'm using 3 here because 3 is my boundary. So I'm adding the area between 1 to 3. And then I'm adding the area from 3 to 5. 3 is my boundary. It's where I'm splitting between the two. And I'll show this when I graph it. I will graph it to show you what's happening there. But this is the only way that you can solve this problem. You go and only solve it by splitting it up into the 2 regions between 1 to 3 and 3 to 5, because I use different functions from 1 to 3. Right? 1 to 3 I use this function, and 3 to 5 I use this function. Right? I can't integrate over the entire thing because I have 2 different functions. Right? And then you'd integrate those 2 pieces. Right? This would come out to be, and again, neither one of these are too bad to do by hand, so I'm going to solve them by hand. X cubed divided by 3 from 1 to 3. Add to that 27 over the natural log of x from 3 to 5. Alright, so this would come out 3 cubed divided by 3, which would be 9, minus 1. 1/3. And then this one's a little messier. 27 natural log of 5 minus 27 natural log of 3. Right, and we'd integrate and find the value there, which comes out to be, make sure I add those up right. So 9 minus 1/3 plus the natural log 27 times the natural log of 5 minus the natural log of 3 comes out 22.459, roughly 22.5. Alright, that's by hand. Alright, now looking at it on the calculator, or looking at it graphically, not on the calculator. Alright, so what that does graphically, so you can see what's happening graphically. Alright, so remember, y equals x squared if x is less than 3. Y equals 27 over x if x is greater than or equal to 3. And so we're looking at the area of this function from 1 to 5. And so when I go to graph this, I'm only going to graph it between 1 to 5. So I'm going to start at 1, x equals 1, and stop at x equals 5. Alright, so I'm going to go, and I'm going to kind of make this a little more like zoomed in, 1 to 5. Remember, 3 is sort of an important moment, so I'm also going to stop there because that's when I switch which function I'm using. Alright, so at x equals 1, I would use the y equals x squared. And so when I plug 1 in, I get 1 out. And so this would be at the point 1, 1. Alright, then if I look at 2, x equals 2, y equals x squared, well, that would give me 4. And so that would put me up here at 2, 4. And then I'm still going to use x equals 3, but remember, this would be an open point. When I plug 3 into my x squared, I would get 9 out. So it would put me up here. So this would be at 3, 9, but this would be an open point. And again, it does have a slight parabola shape to it. And so there would be the piece. that comes from between 1 to 3. And so this would be the first area that we found. Right? The area under my function y equals x squared from 1 to 3. All right, that area would be the 9 minus the 1/3. All right, then the second piece. I'm going to draw the second piece with a different color. And so the second piece, from 3 to 5, well, from 3 to 5, I use the function y equals 27 over x. All right, so again, I do start at 3, and this time it's included because 3 is a part of that function. Well, when I plug 3 into 27 over x, I get 9 out. So I actually do start here at this moment, 3, 9. So I fill that circle in because it starts there. And then I plug 4 in, and it comes out 27 over 4. So again, it would be 4 at 27 over 4, which is not a real pretty number. And the same thing at 5. X equals 5. My y value would be 27 over 5, which is a little smaller. Not a lot smaller. And so again, it would have this, actually it's probably a little closer to the 9 that I have listed up there, but we have this slight curve to it here. This would be the second function from 3 to 5. So this would be the y equals 27 over x. Shade that area in from 0 to 5, which again would be that ugly number that we found, the 27 natural log of x from 5 to 3. Right? And so you'd have to graph the two different functions and find it, but this would be the area between the two. We have to split them between 3 and 5, right? And so we'd find the first area. This is area 1, this is area 2. And so that's what this does. This would be area 1. This would be area 2. I add my two areas up. When I add my two areas up, it comes out to that. And if you do find that graphically, you'd have to graph two functions. You'd have to graph the x squared, find the area from 1 to 3, and then add to that the graph of the second function, which is the 27 over x, and shade that from 3 to 5. Add the two areas up, and you should get the exact same answer that I got by hand. I actually think these are easier by hand because you don't have to graph two things, right? But you can graph them too, solve them either way. Either way is fine for whichever one. If you solve it graphically, you do have to graph two functions. All right, if you solve it by hand, you do have to solve two functions. So again, it's up to you. You can solve it either way. I don't care as long as you show me both of them. All right, so you need to show me what I want to see is this. I know you're solving this, so I want to see this. If you're solving it by hand, you show this that I have here by hand. If you're solving it graphically, well, I want to see this picture. Now, you don't have to have all the numbers that I have, but it should be at least a sketch of this picture when you're graphing. It should resemble something like this because I know that's how you're solving it. All right, we will stop there.